Imagine for a second that you possess a saw, but not just any saw, a saw of godlike proportions.
Okay.
You take this thing to the Himalayas and you cut Mount Everest off right at its base, precisely at sea level.
Right at the bottom.
You harness that massive peak, the absolute highest point on our planet, the roof of the world, and you drag it all the way out to the western Pacific Ocean. You position it over the water and you just let go.
It sinks, obviously. It's rock.
It sinks. It hits the bottom. But here is the terrifying part. If you were floating in a boat right above where you dropped it and you looked down, you wouldn't see the summit breaking the surface.
You wouldn't even be close.
You would still have over a mile, over 2,000 meters of pitch black water swirling above the peak of Everest. That is the sheer vertiginous scale of the abyss we are talking about today.
It really redefines the word deep, doesn't it? I mean, we aren't talking about the deep end of a swimming pool or even the continental shelf. This is the ultimate frontier of Earth.
Welcome back to the Deep Dive. And specifically, I need to welcome you to episode 2 of the Uncomfortable Depths podcast.
Uncomfortable is definitely the operating word for this set of sources.
It is, and I want to be clear about why we're using that branding for this specific dive. First, it's physical. The environment we are going to today is crushing, freezing, and alien. It is physically uncomfortable for biology. But secondly, and I think this is where the sources really surprise me, there are some uncomfortable truths down there. We have this romantic idea of the deep ocean as a pristine, untouched wilderness.
Right, out of sight, out of mind.
Right.
We just assume distance equals protection.
Exactly. But the research we have, from geological surveys to biological studies on snailfish and pollution reports, suggests that remote does not mean protected.
In fact, the data suggests the opposite. That the very shape of this place makes it a trap, a planetary drain.
So our mission today is to explore the Challenger Deep, the deepest point of the Mariana Trench. We're going to figure out how life manages to exist where physics says it basically shouldn't.
And we're going to reveal why this remote scar in the Pacific has become a repository for our industrial mistakes.
So let's start with the container itself. You called it a scar. Geologically speaking, that is incredibly accurate.
It's a wound in the crust, yeah.
Physically, let's orient the listener. We are in the western Pacific, east of the Mariana Islands.
And if you look at a bathymetric map, a map of the ocean floor, it looks like a crescent-shaped gash. It's huge in length, over 1,500 miles long.
Wow.
To put that in perspective, that is longer than the coastline of California.
But the width is what surprised me in the notes. It's not a broad valley?
No, it's surprisingly narrow. It averages only about 43 miles wide. Think of it as a slot canyon on a planetary scale.
And the deepest part, the Challenger Deep, is sitting at approximately 10,984 meters down. That is nearly 7 miles of vertical depth.
Just straight down.
How does a hole that deep actually form? I mean, the Earth is a solid gall of rock, mostly. We aren't hollow. How do you get a gash that goes down 7 miles?
It comes down to the violence of plate tectonics, specifically a process called subduction.
Subduction.
It's a slow-motion crash between two massive slabs of the Earth's crust, the Pacific Plate and the Philippine Sea Plate.
And usually when things crash, they crumple up, right? Like the Himalayas getting pushed up?
That happens when continents crash, when two light plates hit each other.
Yeah.
But here, we have oceanic plates. And the key detail in the geology reports is the age of the Pacific Plate. It is old.
How
We're
old?
talking 180 million years old.
Okay, so why does the age matter for the depth?
Because rock changes as it ages. As it moves away from where it was born, mid-ocean ridges, it cools down. And as rock cools, it contracts, it becomes denser, it gets heavier. But you have this ancient, cold, incredibly heavy Pacific Plate crashing into the lighter Philippine Plate. It doesn't crumple up, it sinks. It dives steeply, almost vertically, plunging into the Earth's mantle.
So the trench isn't just a hole. It's the physical site of the ocean floor dragging itself down into the underworld because of its own weight.
Precisely. That steep dive creates the V-shaped trench. It's effectively the heavy edge of a carpet sliding under the floorboards.
Now, when James Cameron went down there in 2012, and we'll get to the history of the explorers later, he described the bottom as lunar. He called it desolate. It paints a picture of a dead, still world.
Which is a beautiful poetic description, but geologically, it's a bit misleading. It looks still to the human eye, but it is actually a violent place. The sources call it a seismic factory.
Because that plate is still moving.
It's grinding. The sources mention frequent earthquakes, magnitude 4.5 to 8. But here's the visual that really stuck with me. The bottom isn't just jagged rock. It's covered in this superfine sediment.
The researchers compared it to baby powder, right?
Yes. Technically, it's often diatomaceous ooze, the crushed-up skeletons of microscopic sea life that have been raining down for millions of years. It's soft.
So what happens when an earthquake hits?
Well, imagine a desolate moonscape, but every time the ground shakes, which is often, this dust erupts.
Like a shaken snow globe.
Exactly. It gets kicked up into the water column, creates these massive whiteout clouds, and then slowly settles back down like fresh snow.
Which effectively hits the reset button on the landscape.
It does. It hides the tracks of whatever is living down there. It just wipes the slate clean.
That is a spooky image, just silent dust settling in the dark after an earthquake. But you mentioned life, and this is where the dive gets really interesting for me, because if I'm standing at the bottom, aside from the darkness, the pressure is the main event.
It's hard for us surface dwellers to comprehend. We walk around with 1 atmosphere of pressure on us. Down there is over 1,000 atmospheres.
Can we get an analogy for that? Something to wrap my head around.
Okay, imagine you are holding your thumb out. Now imagine an African elephant, a full-grown bull elephant.
Okay.
Now imagine that elephant balancing on 1 leg directly on your thumb.
Unpleasant.
Yeah, that is roughly the pressure at 11,000 meters.
Okay.
It's roughly 8 tons per square inch. It's enough to crush a submarine, like a soda can, if there's even a tiny structural flaw.
It actually compresses the water itself.
It does, making the water at the bottom denser than at the surface.
And yet we aren't just fighting bacteria down there. We are talking about actual complex vertebrates, fish.
The Hadal snailfish, Pseudoleparus swirae.
I looked at the photos included in the source material. I think people expect a deep-sea monster, giant fangs, glowing lights, scary eyes.
Like the anglerfish or the viperfish?
Yeah. But this thing, it looks like a tadpole. Or a raw chicken breast that's been left in the sink too long. It's this pink, gelatinous blob. It looks incredibly fragile.
It's definitely not winning any beauty contests. But physiologically, it is a masterpiece of evolution. It is the deepest dwelling vertebrate ever found, and surviving down to about 8,100 meters.
How does a vertebrate something with bones survive the African elephant on the thumb? Why don't its bones just snap?
Well, the sources outline what they call an extreme survival manual. The first rule is, don't have rigid bones. Their bones are thin and incompletely ossifying.
So they're bendy.
Essentially, they're cartilaginous and flexible. If you built a skyscraper out of rigid concrete in an earthquake zone, it cracks. If you build it to sway, it survives.
The snailfish is built to sway.
Exactly. And I saw a note about the skull being open.
Yes, the skull is partially open. If you had a fully closed, rigid skull, the pressure differential could crush it.
So this way it equalizes the pressure.
Instantly. There's no inside or outside pressure to fight against. The fish is essentially water.
But the structure's only half the battle. The chemistry is where it gets really technical. The sources mention a specific chemical shield.
Right. It involves a molecule called TMAO, trimethylamine N-oxide.
Okay, let's unpack this. Why does a fish need a chemical shield?
Think about what pressure does to proteins. Proteins are the machinery of life. They digest food, they send signals. They are complex, folded shapes, like origami. Their shape dictates their function.
Okay.
Under extreme pressure, water molecules get jammed into those proteins and force them to unfold. They warp.
And if your proteins warp, you die.
Your metabolism stops working. Your cells fail. TMAO is amazing because it binds to water molecules and structures them. It acts like a brace or a scaffold, preventing the water from crushing the protein structure.
A chemical scaffold.
Perfect way to put it. The deeper the fish lives, the more TMAO it needs in its cells.
The notes mentioned a really interesting consequence of this. It's basically brining itself.
It is. TMAO helps manage salinity, and that brings us to the theoretical limit. The sources suggest that fish, as we know them, physically cannot exist deeper than about 8,200 meters.
Because of the osmosis.
Exactly. To fight the pressure at 8,200 meters, a fish would need so much TMAO in its cells that its internal fluids would become saltier than the seawater outside.
And basic biology tells us that water moves from low salt to high salt.
Osmosis would reverse. Water would rush into the fish's cells to try and balance the salt concentration, and the fish would swell and burst.
So the snailfish is living right on the razor's edge of what is physically possible for a vertebrate.
It really is. It's an evolutionary dead end in the best possible way. It has maxed out the stats for depth.
We also have to touch on their senses. No light means no eyes, right?
Well, not no eyes. They have eyes, but they've lost the genes for seeing color because why would you need color vision in pitch blackness?
Right.
But they have retained genes for seeing in dim light, perhaps to spot bioluminescence. But the real surprise is their hearing.
Why would hearing be a challenge at 7 miles down?
It's a chemistry problem again. Fish hear using otoliths hear stones. They are made of calcium carbonate, but below a certain depth, called the carbonate compensation depth, the pressure and acidity cause calcium carbonate to dissolve.
That's why you don't see many shells down there.
Right, so the snailfish has evolved extra copies of a gene called KLAANJ, which supercharges their ability to calcify these stones.
Wow.
They are fighting the ocean chemistry just to keep their ears intact so they can hear prey in the dark.
It's incredible. But the snailfish isn't the only thing down there. The sources mention xenophyophores.
If you want to talk about aliens, this is it. These are single-celled organisms. Protists.
Usually when we say single-celled, we mean microscopic. You need a slide and a lens to see them.
Not these. Xenophyophores can grow to the size of a human fist.
A single cell the size of a fist.
It defies what we think a cell should be. They are incredibly delicate, incredibly abundant, and they sift through that baby powder sediment we talked about earlier.
They are the grazers of the abyss.
And speaking of grazing, we have to talk about the food source. Because usually the food chain starts with the sun, photosynthesis creates plants, animals eat plants, but there is no sun here.
For most of the deep ocean, they rely on marine snow dead stuff falling from above. But in the Serena Deep, near the Challenger Deep, researchers found microbial mats that are doing something else.
Chemosynthesis.
Exactly. They're running on chemosynthesis.
They're eating chemicals directly from the rock.
Specifically, they are feeding on hydrocarbon and sulfur seepage. This is fascinating because it gives us a working model for life on other planets. If you look at the moons of Jupiter or Saturn, like Europa or Enceladus.
Which are ice worlds.
Right. They have icy crusts and likely deep, dark oceans underneath. No sun. But if they have this kind of chemical seepage from their rocky cores, life could exist there, just like it does in the Mariana Trench.
So the trench is basically a test kitchen for alien life. That is a hopeful thought. But, and here comes the twist for this episode, we need to talk about what else those microbes and amphipods are eating.
This is where the story shifts from wonder to the uncomfortable part of our title. We assume the bottom of the trench is pristine because it's so hard for us to get there.
Right.
But physically, remember the shape.
The V shape.
It acts as a funnel, a planetary drain. Gravity pulls everything down the slopes. Dead animals, algae, whale falls. It all slides down to the very bottom.
And it brings our garbage with it.
It amplifies it. This is what the researchers call the funnel effect. The trench becomes a repository. The study on PCBs and PBDEs is frankly shocking.
Just to clarify for the listener, PCBs are industrial chemicals, coolants, lubricants that were banned years ago, and PBDEs are flame retardants.
Right. These are persistent organic pollutants. That word persistent is key. They don't break down.
They just stick around.
They latch onto organic matter, that marine snow, and they sink. When they hit the bottom, they have nowhere else to go.
What kind of levels are we talking about?
The concentration of PCB is found in sediment between 7,000 and 11,000 meters was higher than in some of the most polluted coastal industrial zones, like the Liaohe River system in China.
Wait, let that sink in. The sediment at the most remote place on Earth, 7 miles straight down, has more poison in it than a river running through a factory district.
In some samples, yes.
Yeah.
And it bioaccumulates. Those little shrimp-like scavengers, the amphipods, they eat the contaminated detritus.
Okay.
The chemicals are fat-soluble, so they get stored in the amphipod's body fat.
And because nothing really eats them except maybe the snailfish?
The poison just sits there. It amplifies. The amphipods become toxic little nuggets.
If the animals at 11,000 meters are sick with industrial chemicals, there is no part of the biosphere that is safe.
It really feels that way.
And it's not just invisible chemicals. We have visual proof. The plastic bag.
This was observed in 1998 by a Japanese ROV called Kaiko. At 10,898 meters, almost the absolute bottom, the camera picks something up.
A single-use plastic bag.
Just drifting there.
That is devastating. We managed to get a plastic bag to the bottom of the world before we even really understood how the biology down there works.
It really challenges the concept of remoteness. The trench isn't a wall that keeps things out. It's a drain that pulls things in.
That's a heavy thought, but I want to pivot slightly to the human element. Because getting a plastic bag down there is easy gravity does the work. Getting a human down there, That's a different story.
It's harder than getting to the moon. Far fewer people have done it.
Let's look at the history provided in the notes. It started with the HMS Challenger in 1875, and I love this. They found the trench effectively by accident.
They were doing routine soundings. This was low-tech science. They would drop a weighted hemp rope over the side and measure how long it took to hit bottom.
Just a rope and a weight.
Just a rope. And one day, the rope just didn't stop. It kept paying out, mile after mile. They recorded about 4,475 fathoms, which is roughly 5 miles.
So they knew they'd hit something big.
They knew they'd found a hole, but they had no idea how deep it really went.
Fast forward to 1960. The Cold War is on, the space race is heating up, but there's also a race for the deep. Enter the Trieste.
This is the legendary dive. Jacques Piccard and Don Walsh. The Trieste wasn't a submarine like we think of today. It was a bathyscaphe.
Which basically means an underwater hot air balloon.
Exactly. It was a giant float filled with gasoline.
Why gasoline? That sounds dangerous.
It sounds like a bomb, but it was genius. Gasoline is lighter than water, providing buoyancy, but crucially, it is incompressible.
You can't crush a liquid.
Exactly. If they had used air tanks for buoyancy, the pressure would have crumpled them instantly. So they sat in a tiny steel sphere underneath a giant bag of gasoline.
2 guys crammed in a steel ball for a 5-hour fall.
And it wasn't a smooth ride. About halfway down, they heard a loud cracking sound. A window pane in the entry tunnel had cracked under the pressure.
That has to be the most terrifying sound you can hear at 30,000 feet deep.
But they decided to keep going. They figured if the sphere itself was intact, they were okay.
And when they finally hit the bottom, what did they see? This is the great anticlimax of exploration history.
They landed. And the landing stirred up that baby powder diatomaceous ooze we talked about.
The whiteout.
Total visibility loss. They couldn't take a clean photo. They spent 20 minutes peering out into a cloud of silt, eating chocolate bars, and then they had to drop their lead ballast and head up.
But they did claim to see something, right? A flatfish.
They reported seeing a flatfish, like a sole or flounder, swimming away. But this is a huge point of contention in the scientific community now.
Because of the osmosis limit we talked about earlier?
Exactly.
Yeah.
Biologists are almost certain that fish cannot exist at 11,000 meters. The Trieste was way past the physiological limit for a vertebrate.
So what did they see?
Likely a sea cucumber. Some of them are translucent and flat, and in the stir-up of sediment and the adrenaline of the moment, it's an easy mistake to make.
I feel like if I risked my life in a gasoline balloon to go 7 miles down, I'd want to see a fish too. I'd probably hallucinate a mermaid just to make it worth it.
It took 52 years before another human went back. James Cameron in 2012 in the Deep Sea Challenger. And more recently, the Chinese submersible Fondouge in 2020.
And the Fondouge is doing some really detailed science now, right?
Yes. High-definition imaging, carbon cycling data. We are finally moving past just tagging the bottom to actually studying the ecosystem.
But what they're finding brings us back to that uncomfortable truth. We aren't just finding new species, we're finding our own footprint.
It seems like every time we turn on a light down there, we see something that reflects us back.
That's the paradox of the trench. It recycles carbon, burying it 7 times faster than other parts of the ocean. It's a vital part of the planet's health.
But it also buries our mistakes. It's a bioindicator. If the animals at 11,000 meters are sick, no part of the biosphere is really safe.
So, what does this all mean for the listener? We've covered geology that crashes plates together, fish that survive impossible pressure, and a plastic bag that beat us to the bottom of the world.
I think it demands a change in our mental map of the Earth. We tend to think that if we throw something away, it's gone.
Right.
But in a closed system like Earth, there is no away.
Away is just a place.
And in the ocean, away is just down. Gravity eventually pulls everything to the lowest point. The Mariana Trench proves that the deepest, most remote hiding place on Earth is actually a collection point.
That is a sobering thought. I want to leave you with one final idea to mull over, something that wasn't explicitly in the conclusion of the sources but feels relevant.
Go on.
We talked about subduction, how the trench is where the Earth eats its own crusts, dragging it down into the mantle to melt, and eventually millions of years later recycle it back up through volcanoes.
It's a great geological cycle.
Yeah. If we are now salting that crust with plastic, flame retardants, and industrial chemicals, and the Earth is eating it, what happens millions of years from now when that crust melts and comes back up? Are we effectively changing the geological recipe of the future Earth?
That is a question I don't think we have the answer to yet, but it suggests our legacy might last a lot longer than we think.
Something to think about next time you toss something in the bin. That's it for this deep dive into the uncomfortable depths. Thanks for listening.